Okay, let's jump right in. Today we're doing a deep dive on a huge step forward for generalist AI. It's called Nitrogen.
Right. This is an open foundation model from NVIDIA and a few collaborators, and it really tackles what's been the biggest roadblock for training complex embodied AI agents.
And that roadblock has been around for a long time. We've wanted agents that can learn inside these big interactive worlds for decades, but the research always seemed to hit a wall.
It did. And that wall was a data wall. I mean, progress in this field has been totally choked by the lack of massive, diverse, and this is the key part-labeled action data sets.
So you need to know not just what's on the screen, but exactly what button the player was pressing at that exact moment.
Exactly. And trying to manually label, say, 40,000 hours of gameplay is just, it's impossible.
Which is what makes Nitrogen so wild. It's trained on exactly that, 40,000 hours of gameplay from over 1,000 different games. It's a total game changer.
And the breakthrough was realizing the action labels were, hiding in plain sight.
On the internet. How on earth did they do that?
They found this amazing public data source, gameplay videos that have input overlays.
Oh, you mean those little graphics of a gamepad in the corner that streamers use?
That's the one. Streamers put them there so viewers can see their inputs, but it turns out to be the perfect labeled data set for an AI.
I can't believe a feature for viewer engagement ended up being the key. But, I mean, that video has to be messy, right? Different resolutions, different controllers.
Oh, it's incredibly noisy. So they built this really clever pipeline to clean it up. First, an annotation model finds and crops just the gamepad.
Okay, so it isolates the controller?
Then they use a fine-tuned segmentation model, it's called SegFormer, to basically cut out the joysticks and buttons and predict their state.
And that actually worked from compressed internet video.
It worked incredibly well. We're talking about a 96% average button accuracy and a joystick R-squared score of 0.84. It proved you can get clean data from this noisy source.
Wow. But what about bias? I saw the data is really heavy on action RPGs and platformers.
It's a valid concern, but the sheer scale of 1,000 games helped smooth that out a bit. And the accuracy numbers really gave them the confidence to move forward.
So once they had the data problem solved, what did they build? What's the brain of Nitrogen?
The architecture is a vision action transformer. It's an adaptation of an earlier model, but it's built for speed and generalization.
And it uses a SIGLIP vision encoder, right?
Yes, and crucially, a diffusion transformer, or a DDIT. But instead of generating images, it's been repurposed to generate the sequence of actions based on what it sees.
And it's doing all of this from a single, pretty low-res frame of the game, just 256 by 256 pixels.
Yep. That low resolution is key for efficiency. It lets the model focus on the big picture, not tiny details.
So how do you even test something so general?
That's the other brilliant part.
Here.
They built a multi-game evaluation suite with 30 different tasks across 10 commercial games.
Yeah.
And they used a universal gymnasium API wrapper.
What does that do?
It lets them programmatically control any commercial game without hacking the code. It just simulates perfect player inputs. It's the only way to test for true generalization.
And the model showed strong skills right out of the box, even on games it had never seen.
That's the zero-shot confidence, yeah. But the real headline numbers come from the transfer learning.
Right, because training a model from scratch on a new game is so hard.
It's incredibly data hungry.
Yeah.
But when they took the pre-trained Nitrogen and just fine-tuned it on a new game, the results were amazing.
And what was the result?
Up to a 52% relative improvement in task completion rates compared to a model trained from scratch on that same new game.
52%. That is a massive efficiency boost. It's basically proof that it's learning the common language of gaming.
It is, but with some nuance. It saw huge gains in generic skills, navigation, basic combat. But for really game-specific puzzles or mechanics, the improvement was much smaller.
So it learns the grammar, but it still needs a quick lesson on the local vocabulary for each new game.
That's a perfect way to put it.
So to pull this all together, Nitrogen is this huge open source step forward. It proves we can get past that data bottleneck. But you mentioned it's currently a System 1 sensory model. What does that mean here? Is it just pure reflex?
Precisely. System 1 thinking, in this context, means it's purely reactive. It sees what's on the screen right now and reacts. It can't plan ahead. It can't remember the last room it was in to solve a maze.
And it can't follow language commands like go get the key and bring it back here.
Not at all. It has no long-term memory or planning capability.
So here's the thought we want to leave you with. If Nitrogen has mastered the reactive System 1 behavior for 1,000 games, what's the one ingredient it needs to make the leap? What would it take to turn this world-class reactor into a long-term strategic planner?